Coming to this introduction to semiconductors, generally the materials are classified into the three types broadly, and those three types are: first one is a metal, and next one is a insulator, and in between both these two, here I am writing the semiconductor. So these are the three materials broadly we can classify. Coming to the metals, the materials which provides the highest conductivity is called as a metal. And coming to the insulator, the material which doesn't provide or which provides the least conductivity is called as a insulator. Generally, we represent the conductivity with this notation sigma. So highest conductivity can be called as a metals, and the least conductivity is a insulator. And coming to the semiconductor, whatever the properties, that means a semiconductor material is one whose electrical properties lie exactly in between those of insulators and good conductors. That means depending upon certain conditions, for example, if I'm taking the temperature as a condition, if the temperature is at 0 degree kelvins, then the semiconductor acts like insulator. And if I keep on increasing the temperature, or else let's take T is equal to 300 kelvins, then the same semiconductor acts like a metal. We cannot say that it acts like exact metal, but it acts like a metal. So depending upon this temperature condition, here the semiconductor behaves in the two different ways. T is equal to 0 kelvins acting like an insulator, and at T is equal to 300 kelvins it starts acting like a metal. Coming to the examples of semiconductors. So generally all of you know that the most familiar example to the semiconductor is silicon and germanium. But whatever the fourth group periodic elements in the periodic table, all these fourth group periodic elements are comes under the examples of these semiconductors. So the semiconductors can be defined as those materials which have almost an empty conduction band and almost filled valency band with a very narrow energy gap of 1 electron volt separating the conduction band and valency band. So regarding this conduction band and valency band, we will see in the second topic, that is the energy bands of these semiconductors. But just note this point, that the forbidden energy gap, or the energy gap between the conduction band and the valency band, is very small, and the conduction band is almost empty, and coming to the valency band is almost filled at T is equal to 0 kelvins. So these are the things. And coming to the types of the semiconductors, the next one is it is a one, let's take it as a 1.1, and coming to the 1.2, that is the types of semiconductors. Here the semiconductors can be broadly classified into the two types. The first one is a pure, or it can be called as a intrinsic semiconductor, and the second one is called as an impure, or it's called as an extrinsic semiconductor. And coming to this impure or extrinsic semiconductor, again these are classified into the two types based upon the dopants. One is the N-type semiconductor, and second one is the P-type semiconductor. So it is the types of semiconductors. Now we are going to see in detail about this pure semiconductor, and then we will go to the impure semiconductor. Coming to the pure semiconductor, it's an intrinsic, that means extremely in pure format without having any kind of impurities. So the best examples to this pure semiconductor is germanium or selenium. So these are the best examples to this one, without having any kind of extra dopants or any kind of extra impurities. So if you're taking a silicon crystal, in that silicon crystal, whatever the atoms are there in that crystal, if all the atoms are belongs to silicon only, then it is called as a pure semiconductor or a pure silicon crystal. So it is a type of this one. And one more way to define this intrinsic or pure semiconductor is that generally in the semiconductor we will be having the two types of charge carriers. One is the hole and second one is the electron. So here the most important thing here is that coming to the metals, we are going to explain the conductivity only with respect to the electrons. And in the insulator also conductivity only with respect to the electrons. But in the semiconductor, the conductivity can be explained with respect to the two types of charge carriers. One is the hole and second one is the electron. That means holes are the positively charged carriers and electrons are the negatively charged carriers. And one more clarity is that holes are the virtual charges. That means these are only imaginary charges. So practically the holes are not exist in the semiconductors. But even though not existing, why we are explaining in this concept means we will see that one later. Electrons are the physically existed charge carriers. And coming back to our concept, so here coming to the semiconductor, as I told that semiconductor conductivity can be explained with respect to the two types of charge carriers. One is a positively charged carrier, that is hole, and second one is a negatively charged carrier, that is electron. So if I'm representing the concentration of holes in a semiconductor with NP and the concentration of electrons in a semiconductor is N suffix E, if both these two are equal, then it can be called as an intrinsic semiconductor. That means in a pure or intrinsic semiconductor, it can also be defined as the semiconductor is a one in which the number of conduction electrons is equal to the number of holes. So it is the concept regarding the intrinsic semiconductor. And coming to the next one, it is a impure or extrinsic semiconductor. So next we will go to that one. B. It is a extrinsic. So here I am just elaborating that word into the two words, extra plus intrinsic. So with this word itself you can understand that, as I already explained, intrinsic is nothing but a pure, and here extra. So the extra plus intrinsic can be combinedly called as a extrinsic semiconductor. That means in this extrinsic semiconductor, we are going to dope something else into the pure semiconductor. That something else is called as an extra, and technically these are called as a dopants. And again, these dopants are the two types that I will say later. So coming to this one, whatever the injecting of some other impurities or some other atoms into the intrinsic semiconductor, this process is called as a doping process. And this doping process can be done with the two different types of impurities. That first impurity can be called as a trivalence, and second type of dopants are called as a pentavalence, trivalence and pentavalence. So why we are calling like that? Because trivalence nothing but the atoms which are having the 3 number of valency electrons are called as a trivalence, and the atoms which are having the 5 number of valency electrons are called as a pentavalence. So here valence means, let's take the planetary model of an atom. If it is the outermost orbit of an atom, the electrons which are locating in the outermost orbit of an atom are called as a valency electrons. That means in the trivalent atoms, its outermost orbit is having the 3 number of valence electrons. Similarly, while coming to the pentavalent, it will be having the 5 number of valency electrons. Coming to the semiconductor can be called as a tetravalent atom. Why? Because in a semiconductor, it is having the 4 number of valency electrons. So it is the concept regarding this trivalence and pentavalence. Now we will see the examples to both these two. While coming to the trivalence, indium, gallium, boron are the examples, and coming to the pentavalence, arsenic, antimony, phosphorus are the examples. So out of this trivalence, boron is the most used one, And coming to this one, antimony or sometimes the phosphorus is the most commonly used dopant. And if we dope the trivalent atoms into the pure semiconductor, then it is called as a p-type. And if we dope the pentavalent impurities or atoms into the intrinsic semiconductor, then it is called as an n-type semiconductor. So why we are calling like this? Because so if we are doping the uh, trivalent impurities into the pure semiconductor, so after doping, it will be the equivalent atomic structure. That what it means is that this type of semiconductor is obtained when traces of trivalent like boron are added to a pure germanium crystal. In this case, the three valency electrons of boron atom, three valency electrons, let's take it is the 1 and 2 and 3, these three are recording the boron. So these three valence electrons of boron atom forms covalent bonds with surrounding four valency electrons of the germanium atom. Say it is one valency electron of the germanium, it is one, it is one, and it is one. That means while coming to the boron, so this side two valence electrons and here two and here two, but here only one valence electron is there, that is recording the germanium, but here there is no electron to the boron. Why? Because boron is a trivalent, it must have only the three valency electrons. So now totally how many valence electrons are there, including the shared one? The total becomes is equal to 2 plus 2 plus 2 plus 1, that is total 7 number of valence electrons are there. To become stable for any one atom, it requires total 8 number of valence electrons. Now this central boron atom got only the 7 number of valence electrons, and it is continuously waiting for the one more electron to get the stability. So that's why boron or the trivalent impurities are called as acceptor impurities, which are always ready to accept one electron to become the stable. So that's why here one more thing is that the trivalent impurities are also called as a acceptor impurities. Why we are calling like this? Because they are always ready to accept one electron to become the stable. And whatever the place of a vacancy of electron here is there, this vacancy of electron, this position always try to accept one electron. That means it is trying to attract the one negatively charged particle. If it is trying to attract one negatively charged particle, means this particle, this position must have the positive charge. Why? Because the unlike charges will attract it with each other. So here we are calling this one as a hole, which is nothing but a vacancy of one electron, and holes are having the positively charged things. So here for each and every one boron atom, I am getting one hole. If I am doping the more number of trivalent impurities, then I am going to get the more number of holes. So more number of holes leads to the positive charge. So that means here in the p-type, the majority charge carriers are the holes or the positively charged particles. And why we are calling this one as a p-type means, so here if more number of holes are there by doping the more number of trivalent impurities, I said that these holes are having the positive charge, and the starting alphabet of this positive charge is a p. So that is how I'm thinking that we're going to call it as a p-type. The same concept can also be explained for this p-type is that if I'm doping a trivalent atom into the semiconductor, as I told that semiconductor is a tetravalent, then so trivalent plus tetravalent, that means 3 valence electrons plus 4 valence electrons, it becomes is equal to 7. So 7 number of valence electrons that a central boron atom will get, it requires one more electron to become the stable. So this concept also can be compensated to this concept. So both these two are same. So this concept is worked out for the mathematical thing, and this concept is worked out for the atomic structure wise. So here trivalent impurities can be called as a acceptor impurities.